Hello, sophomore chemistry. Today I want to review homework number 1 over the different types of intermolecular forces. Tomorrow I will post videos for homework numbers 2 and 3 in preparation for the upcoming quiz, which will be on Monday, the second quiz. And then on Tuesday we'll review those quizzes, and then a week from today we will take our Unit 10 exam. At least that's the plan. So first, again, everyone turn this in, and if you turned it in on time and if you turned it in complete, you made a 100 and you can pat yourself on the back. But if you want to know like how fantastic you actually did, well then what you should do is pull up your homework, because I didn't go through all 100 and match all like 20 bubbles to make sure everyone got it perfect. So here is your answer key. And I guess I could just post an answer key, but I don't know. I just wanted to hear my voice some more. So here we go. So first, what is an intramolecular force? So intra means internal. And when we talk about intramolecular forces, those are more specifically covalent bonds. And so it's the forces that hold atoms together in a molecule. So this is from Unit 9, ionic bonds, covalent bonds. So it's the things that hold atoms together. Now, in this chapter, we're interested in intermolecular. And so inter means between. And so specifically here, an intermolecular force is some type of force that holds separate molecules together. So again, if water is a liquid, it's because separate water molecules are held together by intermolecular forces. Which of the two forces is stronger? Intramolecular is significantly stronger. It takes a lot more energy to break an intramolecular force. Again, we consider that a chemical reaction, but intermolecular forces are much weaker. In the notes I talked about, if two people are holding hands and we want to separate them, we could easily break their hands apart, or we could rip somebody's arm off, and it would take more energy to rip that arm off. That would be equivalent to the intramolecular. The intermolecular forces we're interested in are much more reversible, because the energies for them to be broken but then also come together are much smaller. So again, when we talk about the fluidity of liquids, like between water, it's because there's forces that are holding them together, but not so strongly that they're locked strictly in place. What's the boiling point have to do with them? So they are directly related. So meaning as one goes up, so as intermolecular forces get stronger, the boiling point goes up, increases. So to boil something like water, you have to break all the intermolecular forces. And if those forces get stronger, the boiling point goes up. So something like ammonia, instead of boiling at 100, it only boils at like 70, indicating its intermolecular forces are weaker. What kind of intermolecular force do you have with water when it's dissolving an ionic compound like table salt? So we looked at 4 different kinds of intermolecular forces, and there was only one of them that had to have a mixture. And so this is a mixture of water and table salt, water plus salt. And what's notable is we have something polar and something charged, or an ion. And so there was one that was specifically called an ion dipole force. There we go. That's it. So ion is something charged, like an ionic compound. A dipole refers to something that's polar, that has a permanent dipole, and it is an attractive force. So any ionic compound dissolved in a polar solution, it's ionic dipole forces. Which of these molecules would have a larger boiling point, and why? So I suppose you could just Google and say, hey Siri, what's the boiling point of octane, or what's the boiling point of pentane? And it's easy to get an answer, and it's going to tell you octane is higher, but we want to know why. So what's significant is that since both of these are carbon and hydrogen, they are both non-polar. Both non-polar. And if they're non-polar, then they're held together by London dispersion forces. And London dispersion forces are the weakest of the intermolecular forces. And we talked about one of the things that does make them stronger is the more polarizable. And we get that with more electrons. So octane has more atoms, thus more electrons, and so it makes it more polarizable. And the more electrons it can have to be temporarily polarized, the greater the boiling point. Which three atoms need to be covalently bonded to hydrogen for a hydrogen bond? So it's got to be hydrogen bonded to either nitrogen, or hydrogen bonded to oxygen, or hydrogen bonded to fluorine. These are the three NOF most electronegative element. And so what it leads to is the greatest partial positives for hydrogen, and the greatest partial negatives for the other three. And so it produces the greatest polar bonds that's going to yield what we call a hydrogen bond. Now, whenever we show a hydrogen bond, we use these three red dots seen here. And what it always has to have is one of these hydrogens on either NOF, and then that should have three red dots to another nitrogen, oxygen, or fluorine. So it says which one is not shown correctly. If we look at the first one, this one checks out. Here's a polar oxygen, which would be partial negative because it's pulling electrons from carbon. And here's a hydrogen on oxygen. So partial positive, partial negative, check. Here we have a polar oxygen, and it's going to a hydrogen. So at first glance, this one looks fine, but it's not. So the middle one is not correct. And what's not correct is the hydrogen that's involved is not directly bonded to either N, O, or F. So there is a hydrogen and a nitrogen, but unless the hydrogen is specifically on it, it's not going to be able to form hydrogen bonds. So both of these are polar. We would say this is dipole-dipole interaction, but it's not nearly as strong as if it could what we would call hydrogen bond. And this third one, this one's good. This is methylamine. It's got a hydrogen on a nitrogen and going to an oxygen. So partial negative, partial positive. This one's good. What major intermolecular force could these interact with water? So first, we have HCl. We need to know that this thing is polar. So because it is polar, we can then say that it can form dipole interactions. Here we have magnesium chloride, and it's ionic. And because it's ionic, it can form ion dipole forces with water. And then here we have something that's nonpolar. And we wouldn't normally say that what is this? This is pentane. Pentane would not interact very well with water. We talked briefly about how it can form a induced dipole moment. So water can cause some of the pentane to be temporarily polarized, and that is attractive, but it's going to be very, 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 very weak. So if you were to look at mixing them together, there would be some measurable amount of them mixing, but for the large part, they won't. But the parts that do mix, we would still call that a London dispersion force. And then finally, we have NH3, where ammonia has nitrogen on hydrogen, and that can hydrogen bond, and water can hydrogen bond. So this one is capable of hydrogen bonding. Next, we want to know, instead of mixing with water, what about just them by themselves? So what if we have, this is methanol. If you have liquid methanol, then what would be the intermolecular force holding it together? So we have oxygen and hydrogen. So anytime you have one of those electronegative elements, something in the top right, you can know that if it's bonded to not itself, like carbon, that this bond is polar. And because it's polar, we could say at the very least dipole-dipole. But because it also has oxygen and hydrogen bonded together, this thing is able to hydrogen bond, which is the strongest. Here we have neon. Now, if you want to get liquid neon, you're going to have to get it down really, really cold to like negative 250 degrees Celsius. It's really cold. And the reason its boiling point is so low is because with single atoms, its polarizability is super duper low. And to get those weak forces to cling them, to get them to grab onto each other, you can't have very much energy. And so this is a strong indicator that it is a London dispersion force, LDF. Here we have formaldehyde. Now, just like methanol, it's polar because oxygen is pulling electron density away from this carbon, and it does have hydrogen and oxygen, just like methanol. However, the hydrogen is not directly on the oxygen. So this is not capable of hydrogen bonding, and we would call this one instead just a dipole-dipole interaction. Here we have methane, which is super symmetric. None of the bonds are polar. Carbon and hydrogen is so methane, none of the bonds are polar, and even if they were, because of symmetry, it's nonpolar. So anytime it's nonpolar, you can automatically know that's a London dispersion force, which are the weakest of the forces. So it's why its boiling point is down at like negative 180. Bromine, they're electronegative atoms, and bonded to something of lesser electronegativity like carbon or bromine, it would be polar, but bonded to itself, it's nonpolar. So again, it's a London dispersion force. So if we want to know which one would have the highest boiling point and the lowest, to answer the highest, we just need to know which one has the strongest type of intermolecular force, and it's the first one. I guess I don't know. Yeah, and that's methanol, or you could put CH4O. And then for the lowest, now there's three that have LDF, London dispersion force. However, we talked about how can you differentiate between multiple nonpolar things, and it's polarizability. So just like this question up here between octane and pentane, the smaller one will have the lowest boiling point. So bromine atoms are pretty large and have tons of electrons. Um, methane Methane is CH4. It's got, let's see, 16 electrons, but neon only has 10. So it's the lightest, it has the fewest. So it's the smallest non-polar molecule. And so its boiling point is like negative 250 compared to negative 180. What are the van der Waal forces? It's a category of the weakest intermolecular forces, and specifically they exclude hydrogen bonds as well as anything with ion. So ion dipole or induced, anything with charges. Um, and we said if you're in biochemistry or biology, they're more commonly going to, instead of say dipole dipole or London dispersion, you're more likely to hear them say van der Waal forces. Um, Contrast the relative strength. Now, again, this question probably in my to criticize myself should have came way up here so that you were thinking about their relative strength before I asked about relative melting point. But it's hydrogen bonding, H bonding is the strongest, followed by dipole dipole, followed by London dispersion force. And that's it for today. Again, as soon as I still haven't released, well, I probably will soon, but I still have some people that for whatever reason have not taken the last quiz. And so as soon as the last people take the quiz, I'm going to release those. Again, so there's the next quiz is coming up very soon. So I will have a review video for the second and third homework assignments. I'll probably put out both of them, one of them maybe even later today, and then the last one at least at some point Friday or by Friday morning. And then we'll have a quiz on Monday. Then there's just more review. On Tuesday, we'll go over the quizzes, test Thursday, and we'll move on to the very, 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 very last chapter. Have a good